lesson 2 is about chemical bonds. We've seen the elements, but these bad boys, they hook together to make contact. And you have oxygen, and you have hydrogen, and when they hook up, they can make water. And what I have on there, that is a structural, not chemical. If you can see glucose with the bonds, that's how it's going to look. I don't even know that myself. I couldn't draw that picture if I had to. I want you to realize that everything's put together. But you notice, all the rivers are oxygen. Look at all of them. How many lines come off the rivers?
2.
See any 3s? See any 1s? That's because oxygen is in element in number 6. He wants 8, right? How many more will he get? That's why he got 2 lines. He's getting 2 electrons. Now, look at the hydrogen. All the hydrogens, how many lines? Only 1. He just needs 1. He will get it. The black ones are carbon. How many lines?
4.
But count again.
4.
Always 4. Carbon is in family number 4, meaning he needs 4 electrons. He's getting 4 every time. That's the beauty of that. They hook up just right. All the carbons, they get their 4. All the oxygens, they get their 2. All the hydrogens, they get their 1. Now, we write it this way. If you count the reds, there's 6 of them. If you count the H's, there are 12 of them. If you count the blacks, there's 6 of them. Do you see a circle right there?
Yeah.
You see it like a dog leg hanging up? That's glucose. There's a circle, it's a penta, it's a circle of 5, and off number 1 is sticking number 6. 1, 2, 3, 4, 5, 6. It's not just a big round circle, like a lot of folks draw. Now, if I rearrange this, I can still get the same formula, but then I have another sugar. That's called fructose, found in apples and oranges and watermelons. If I rearrange that, I'll still have my C6H12, whatever. Then I have galactose, which is found in milk. So I can rearrange those reds and blacks and white marbles, and I still have my formula. But when you rearrange them, you got another thing. So let's go ahead and start the show. So I left it like that on purpose so you can add up yourself. If you look at the blacks, you'll have how many? 6. If you look at the H's, if you count them with your hand, there'll be 12. And if you count the red ones, there'll be 6. And if you look at it carefully, how many carbons are on there? With those 12 H's and 6 O's, how many waters could I make with those 12 H's and 6 O's? How many waters could I make? I can make 6 of them. Now one of them is what? H2O. I got enough right there to make 6. But look at this. How many carbons are there?
6.
This is a carbohydrate. 1 carbon per water. If I got 6 carbons, guess what? I got 6 waters. And that's why I said H12O6. That's my 6 waters. What if the carbon were 10? C10, what the rest of it be? C10, H. I need 10 waters.
It's 5.
H20, O would be 10. That's going to give me 1 carbon per water. C, H2O, C, H2O, C, H2O, 10 times. But you can write it compressed by just saying C6, and those 10 oxygen, those 10 waters, just say H20O10. Because what do you think carbohydrate means? The word means carbon hydrated. If you hydrate something, what do? You add water. A carbohydrate, the word actually means one carbon and one water. If I got 6 carbons, I gotta have 6 waters. And that's what the H12 means. That's my 6 waters right there. Okay? Now, a bond is an attraction, as you know. And atoms can either share electrons or they can give them away. You see my 4 kinds of bonds at the very end of it? Ionic, covalent, polar. Some people would take polar covalent and they put it under covalent. I debated whether to do that or not, but there's enough to say about polar covalent. I give it its own rank by itself. But obviously, polar covalent is a kind of covalent bond. That shouldn't be anything to throw you off. And you see where it says the bonds can be formed by sharing of electrons, that's one way, or a transfer, that's the other way. If you share, what's it mean to cooperate?
Work together.
Work together, right? Do you remember, what name do you give to the electrons in the last ring? There's a word for it, it's a V word. They're called valence electrons. The last ring, that's what we care about. We don't care about the other ones. If there are 4 electrons in that last ring, then his valence number is 4. He's got 4 valence electrons. If there's 2 out there, then the number is 2. Now, if you're covalent, do I give you my valence electrons or do I share them? Covalent means you share. Ions are formed by, here, you can have them, I don't want them anymore. I give them to you. Transferring is where you're making ions, because if I give you some electrons and I lose them, I'm going to become positive, aren't I? But if I pick up some electrons I didn't have before, what do I become then? Negative. So if you give them to me and make me become negative and I stick to you because of it, well, that's an ionic bond. But if you say, no, I got 6 and you got 6 and you can't have mine, I can't have yours, but we'll get side by side and we'll share it together. 2 of yours circle me. I'll look out my window, I see 8 out there going around. Of course, 2 of yours. You look out your window, you see 8 also. It's a good, strong bond. As a matter of fact, if you pour salt into water, what's the salt do?
It dissolves.
Dissolve. Salt is an ionic bond. Because water gets inside there, separates themselves. Y'all get back apart now. Get back to electrons, and they become ions. You ever put chewing gum in water? Does it dissolve? That's a covalent bond, buddy. You don't break down covalent bonds. If you stand in a tub of water, do you dissolve? No. What dissolves off your body? The salt from your sweat. Things like that. If you dissolve, that'd be a problem with it. So you are made of covalent bonds. So you don't dissolve in the water. However now, could you be eaten by a bear?
Yeah.
How does he break you down then?
Tear you up.
Now, if you're made of covalent bonds and you won't break down, how does he do it? He does it.
He's not.
Doesn't matter. When you eat steak or you eat black-eyed peas, those are covalent bonds also because they don't dissolve in water, but they dissolve in you because you provide the water, but you have one more thing else. What do your pancreas makes?
Enzymes.
That makes digestion go.
Enzymes.
Those enzymes. The enzymes make it possible to break down those covalent bonds. Without the enzymes, what you ate would come right and commode, and you die from getting no food. And when you have dinner time, was it beer or wine or water or tea or Coke or Sprite, you need water because if you don't, you're going to get thirsty. If you swing by, if you leave here, go back and get your order of French fries, just tide you over. You don't have nothing to drink. And you get home, your mouth is dry. You're thirsty. Go to again, and usually go and get some water right away. When you're breaking that French fry down, the water, you're going to get the water from your blood. That's going to dry your mouth. That signals you to do what? Drink some water. Dry mouth is what the body uses to signal you to drink some water. Visit the water fountain out there. So, we're going to talk about more about these on my next slides. Ionic bonds, you know a lot about those already. And there's that word electronegativity. If you have 1, 2, or 3, well, you need 7, 6, or 5 more, right? You have low electronegativity if you don't have more than half your shell. If you got 7 already, you need 1 more, you have a high electronegativity. You're drawing hard to get that electron. And then the word valence again. And again, that's just the electrons in that last circle you draw. But that's the one that make it. If that circle is already full, he won't react. That's that. These over here on the side, these over here have full shells. They don't react. They're all gases. Krypton, that one Superman's scared of, that rock, ain't a rock. It's a gas. The author of Superman's series liked the word krypton because it was green. And when he wrote the book, he turned it into a rock. It's not a rock. It won't harm me for it if you know either. But the way he wrote the book, Superman came from a planet called Krypton, which was the green planet. Does not exist. And when the planet blew up, his father stuck him in a spaceship and lost him in space. Superman landed here on the Earth where he has superpowers. And the only thing that can bring him down is what? A piece of his home planet, which is Krypton. All the shows are about Krypton. That's the only thing. What can he not see through? What can he not see through? Lead. The guy who wrote that book, he knew some chemistry. But he missed the boat when he said Krypton rock. It's a gas. You got to freeze that bad boy so far down to make it be a rock, it'd be impossible almost. But he liked the word Krypton. He could use the word neon or radon, but I think Krypton just stuck with him. But these have full shells. They have full valence numbers. They don't want to react. They're not going to react. However, if you're on this side, you have 1, 2, or 3. If you're on this side, you have almost full, maybe 5, 6, or 7 in your last shell already. These have low, because they're almost empty, electronegativity. These have high, because they're almost full, electro. These love to marry these, because I got 2 electrons giveaway. He said, give them to me. And when they do, they come plus negative, and they stick together. The most common one you know is sodium chloride. There's also sodium nitride, sodium iodide. They'll go back and forth. There's calcium chloride. They go back and forth, and you always write the +1 first. That's the rule. You never say chlorine sodium. You always say sodium chloride. You always, always, always write the plus member first. And you say it first too. Sodium chloride. Calcium iodide. Beryllium phosphide. These are the pluses. You always say them first. And write them first too. These are the negatives. You always say them last. And write those last two. So ionic bonding, there's a transfer of electrons, usually 1, 2, or 3. That's ions. So when your ions form, you have a charge. And like I said, if I gave you 2 electrons, well, when I lose them, I become positive. When you pick them up, you become, and that's the bond for me. Then we're going to stick together. But you drop us in water, we're going to separate. And I'm going to be by myself again, and you by yourself again. Ionic bonds are not strong bonds. They're not strong bonds as bonds go, because you put in water and they separate. When you take a bath, you know what dog licks you? Because he loves you. You have salt on your surface. He loves that salt. That's why he licks you for. Now, the one that we use, and not just me, we always use it, is sodium chloride. It has one valence electron. More than happy to give it away. Chlorine, he's got 7. He needs one. He said, yeah, I'll take that from you. You ever comb your hair and pick up paper with your comb? That same thing happened. When you comb your hair, you're depositing electrons. The paper is plus. When you come down to it, the negative comb picks up the positive paper. It's going to fall off eventually and be gone. When the electrons are all gone, it's no longer gone. You got to comb your hair again, do it again. But it's like static electricity. And the attraction it's good, but it's not super strong. If you're going to build something, don't build out ionic bonds, because a good rainstorm, it'll be gone. You got a picture? Agree? This is my rendition of sodium giving electron to calcium chlorine. But if you look down here, what's wrong with the way I wrote that sodium symbol? I just saw it. What's wrong with it? The big A, that's a major error, and I got to fix that because it's going to drive me nuts now. I don't think I can fix it. I think that's part of my picture. Yeah, I got to go back and actually change the picture. But this A, I can't do anything with it.
Did you create the image? Or?
I created all of it.
Oh.
So I'll go back and I'll take this A, drag it down, drop it here, and I have my A right. I can fix it simply, but not here at school. But I want you to realize, I made a major mistake on that one. I was so busy drawing the picture, I forgot to say a big A there. Oh man, you don't ever write a second letter as a big letter. I don't think I'll leave it there, because sometimes I leave things on for teaching reasons. I might leave that there also, just so you know I screwed up. Folks think I'm perfect. Can you believe that? My wife knows better. Anyway, I might leave it alone so I can have something to talk about. You never write the second letter big. Never. That's a major error, and any professor would mark me wrong for saying that. I'd mark me wrong too. I just did, really. All right. So what happens, the sodium gave his electron to chlorine. Now they're both happy. But sodium is now a plus charge, chlorine is now negative, and that's why they're sticking together. That's the bond. That is an ionic bond, when two ions are formed. There's another way of looking at them, much more complicated than the one I did. I got that from the internet probably somewhere. I didn't make that, I know. I want to throw a word at you called cation. And I got Bobby Tebru had to remember it. I'll share it with you in a minute. Because I never can remember a cation, whether it's plus or negative. And now I got a rule I follow in my head that keeps it straight for me. Would you consider a hurricane to be a catastrophe?
Yeah.
You figure there's loss of life in that? That's my rule. Cata, I think a catastrophe. I think of folks losing their lives. A cation lost an electron. That's my kicker. The cation, I think of the word catastrophe. I think of loss of life. And I put it together and say, a cation doesn't lose its life, he loses electrons. Now, if you lose an electron, what do you become though? You become positive. Now, remember that now. If you lose an electron, then you will become positive because you lost that thing making you nothing. Now, I also got a rule for the anion, but I don't like the other rule. You see that second N in there? In anion, the first N? I associate that N with the word, with a negative word. And I'm thinking, an anion is negative. Why is he negative? What did he do? Did he lose a proton or gain an electron? He gained an electron. But I still prefer my catastrophe. I use that one. Then I know that one, I know the other by default. Cation is always smaller. Because the anion has done what? He gained electrons. He's going to be bigger. Because you pick one up, it's going to be bigger always. That's the rule. Makes sense to me. The picture is what many textbooks show you. Right here, it's saying that he's got one he don't want, and he's missing one right here. When this goes, the outside circle's gone, and this circle right here is what you're seeing. And now, this circle is full. But the thing about it is, he lost an electron he's born with. He now has 10 electrons and 11 protons. He's plus one over. This bad boy picked up an electron he's supposed to have, and that's negative, therefore he's negative. These are the ions, notice the full outer rings. And they don't care whether I want to give it away or pick it up, but they both have. Now, this plus and this negative, it will stick together. And that becomes sodium chloride. Sodium and chlorine chemically combine to form, both these will kill you dead. By themselves, they'll kill you dead. They're deadly poison by themselves. Yeah, in a chemical compound, the properties change so much, you just put it in your French fries and eat it. The thing about chemistry is they always change properties. You figure, hey, if I got arsenic and I got this poison, I put them together, I have double poison. Not always. They might become all right. Right here, sodium by itself, kill you dead. Chlorine gas, kill you dead. But when you combine those chemically, everything changes. No, they're not deadly. They're part of your diet. Now you take them apart again, they're in your body. You take them apart, the body has an undercut, because that could turn around and kill you, didn't it? When the body takes them apart, the sodium part, the ion, the sodium part, is sent to your nerves and sent to your muscles to make them work right. The chlorine part is sent to your stomach. The stomach needs that to make that acid called hydrochloric acid. You need those products. But as long as they're hooked together, you can't use either one of them. When you digest them, and they separate, and I can use the sodium, I can use the chlorine. That's all you ever do is you separate and use the parts. But now if you have too much sodium, that also draws water. And the sodium in your bloodstream draws water in your bloodstream, and your blood pressure goes sky high. That in turn will kill your kidneys. And the first thing doctor, as you know, tells you with the high blood pressure is lay off the salt. Lay off the salt, yes.
Okay, so what about if if you're very physically active and you do a lot of PT and you're told to drink like salt water or eat like really salty foods?
If you're very active, you'll metabolize it.
So it won't hurt you?
Not to a degree it won't.
Okay.
But
More
you can't
just let it out or something?
Can you drink salt water? If you're in the ocean and you're on your boat sunk and you're on your raft, can you drink salt water? It'll kill you dead.
Yeah.
So how do you solve that problem? You pray for rain. You pray for rain, because rain is what?
Fresh water.
How do you capture it though?
Open your mouth.
That ain't gonna work. Make some kind of funnel.
Would it be safe though to do that as long as you're physically active like that?
I wouldn't overdo it. I would use Gatorade, those kind of things. I would use a product made for that purpose. I wouldn't use salt water. That's me personally. I would drink Gatorade. Because Gatorade has more than just salt. It's got other ions in it too. See, it has ions in it. You know where Gatorade came from, the name, don't you?
Wasn't it like
Who first developed it?
Florida Gators?
A chemist at the University of Florida. They gave it to the Florida football team, Gatorade. And they shared it with everybody else. I wonder if they had copyrighted that, could they have said, ain't no Georgia aid, ain't no California aid, it's just Gatorade. Could they do that? Well, I guess the guy who developed it was not thinking about the football team, but thinking about people's health. And there are more things. There now, there's Powerade, that same thing. But Gatorade, the folk from where the name came from, it came from University of Florida. That chemist made that drink for those football players in Florida, where it's real hot. And of course, you can buy it now, Winn-Dixie and same stores, the money back. But that's out. Gatorade is called it was designed for the Florida football team. Little history lesson for you. Covalent bonds, man, they're strong. It takes enzymes to pry those suckers apart. And I'm reteaching some things like the valence number, the valence. I want to say it enough times that it sink into you. I don't believe in saying one thing once and then never again. I say it over and over again. And the things you hear me repeating are things you better learn for a test. I ain't just talking to type things on my screen. Now there's no transfer, right? They're sharing. They're just sharing. When you get done blanking, I want to ask you a question. Fill in the blanks, I want to ask something. See if you remember back to the previous slide. Here's a question. Any atom with the last shell almost full, is that low or high electronegativity? High. If you're almost empty, that is low. Now, if here we are, we're both high electronegatives. I ain't giving her mine, and she ain't giving me hers. Because we're such high electronegative. I mean, I have 6. I can make it work if I give one more away, huh? That'd be kind of stupid. I need just 2 more. She might need 1 more. It might be oxygen and chlorine. And when neither one's going to say, you can have, no. But I will get beside you and let some of mine circle you, if you will let some of yours circle me. So I'll look outside and I'll go, I got a full shell. Even though 2 of them are not mine, they're hers. She'll look outside and she'll see 1 go around hers. Well, now the problem is though, if I need to borrow 2, and she has 1 available, I need 2 of her, 1. I need 2 of her. So I can share it. She'll look outside and she'll be happy. The other one will look outside and she'll be happy. And I'll look outside and I think, and I'm happy. That's a strong, but we're sharing, strong covalent bond. And we have to have similar electronegativities. There's no way, if I'm a low electronegative, I want to share. She must snatch away from me. I can't share one with her. She's going to take it. Stingy. I ain't got the power to hold it back, do I? If I'm low electronegative. But that means we're going to be ionic bonding then, though. I'm saying, take that sucker. I don't want her. But then when she does, we stick together because now she's plus. She's negative and I'm plus. But if I have 6 and she has 6, or I got 5 and she's got 5 and I ain't giving none away and she ain't giving none away, the only solution is side by side and share. Cooperate. Covalent bond. It works beautifully. But the bond, you put us in water, we stay together. Water don't bother us. Chewing gum, that's a covalent bond. The enzyme don't break that sucker down. The enzyme is the crowbar that lets water get in there and break us up. Without the crowbar though, water won't bother us. We just stay together in the water. Covalent bonds. This is kind of how it looks with ethane. It's a fuel source for many cooking stoves. All those bonds, when they break, they produce energy. That's the flame that cooks your wiener or cooks your marshmallow or whatever you're cooking. Now, let me show you something. This is the attraction. There's the atom. There's the atom. There's the atom. There's an atom. There's an atom. Atom. You see the 6 H's? You see the 2 C's? That's what you got. Now, this carbon, he's in family 4. He must share 4. And look, he's sharing 4. This carbon, he feels good too, even though they're sharing each other, right? This hydrogen, he has 1. He got to share 1. That's your 1 bond. This is a picture of the electromagnetic fields of this compound, C2H6, called ethane. But again, everything's being shared. Everything's being shared. And that's how that works. Carbon loves covalent bonds. He's got 4. He can go either way, really. I can give you 4. I can share 4. But carbon, there's a whole branch of chemistry called organic chemistry. It only deals with carbon compounds. That's a whole year of study right there. I like inorganic chemistry. Short molecules, small molecules. Organic chemistry, if you think you love chemistry, it will let you know if you love it or not. Because that will drive you through the wall. Most of my science classes I took in college, I cruised through. Very easy. I took organic chemistry. Boy, I was crawling, trying to remember the stuff. And I got a decent memory, photographic memory. But the thing about this thing, I like rules. In organic, there's no rules. It's like I before E except after C. That's all organic is. This compound, except if you have this compound here. You got to remember all these little rules. And I go, you folks who teach this chemistry, you're sick. You're sick. How do you like this stuff? But everyone's got a niche, right? Well, a lot of folks say, why I'm in biology. I didn't happen to like it. My wife can't stand biology. I eat it up. I try to teach her and share my feelings sometimes. She's a business major. Now, as far as all them numbers and crunching, she can have it. But in our household, Bobby, there's a bug back here. My job's to get that bug and kill it. Because she ain't going to. I heard her get a shower today, heard her yell, there! There's a bug. She that weighs about 100 pounds. Bug can't hurt her. Unless she hop around that, I don't know. I'll go get the bug. Polar covalent. Now, you heard about covalent bonds and covalent bonds. Now we got colors. They share, but one of them's a hog. And that the electrons stay around the hog more than the other one. That's a polar covalent. If you share them equally, you're just covalent. I mean, it's like when you have a custody fight for a child. And the mama has more than daddy does, that'd be polar. But both have an equal amount of time, that'd be just plain. That would be polar. This case right here, they're sharing the electrons, yeah. But one of them gets the electrons 5 days of the week and the other gets only 2 days. That's polar covalent. Yeah, they're sharing, but it ain't equal to. If you remember in ionic bonds, that negative electron stays with her and not me. In a polar covalent bond we're sharing, they stay with her more. They'll come by me now and then, they stay by her more. They'll come by me now and then. So it's kind of like ionic in that she is more negative than I am, but I do get to see them now and then. So I'm still covalent. Now, if we're the same, if we're both oxygen, and we see them exactly the same, would that be polar? No, they're the same. But if I'm one atom and she's another one, and she gets them all the time, and I get them on weekends, that's polar. Oh, we're sharing. It ain't equal though. At this time you have when they have different electronegativities. And the hydroxide ion I talked to you about is the best example of this. Polar hydrogen has got a low electronegativity draw. Oxygen has a strong draw. So the electrons circle hydrogen much more than circle hydrogen. That's a polar. They're still sharing, but hydrogen is getting just now and then. Oxygen's always got it. That's a polar covalent bond. I'm going to look ahead a minute. I didn't show you a picture. I might show you one later on. But I wanted to let you know that, I tell you that you have H and you have OH, and they come together to make water. I said the H is positive and the OH is negative. But they're sharing. But the OH has a stronger draw than the H does. So the electrons will circle OH 8 times and circle M twice. OH, M twice. Well, who's got a stronger draw? The OH or the H? Well, the OH has a stronger draw. That is an example of a polar covalent bond. The OH, even though he acts like a single unit, he has them all the time. But then again, that's why OH is such a good reactant. Because you got sodium hydroxide, that's OH. Calcium hydroxide, oh, that's another base. Strong bases, powerful bases. All right, next one. Water is a polar covalent bonded molecule. The electrons spin more time around the OH than the H of H2O. Whenever another polar covalent bond finds water, it separates that. So which is stronger? A covalent bond or a polar covalent bond? Which one's more likely not to separate in water? The covalent or the polar covalent? Covalent. Covalent bonds are extremely strong, they're equal attraction, but here a polar covalent bond is, I kind of like you anyway. You didn't have an electron 2 times, you got it 20 times. So we get in water, it's also polar, it gets in between us and breaks us up. But now we're sharing things equally, we got a good firm grip, we're not going to let go. So polar covalent bonds, I took them separate because the covalent bonds are nice, they're awful strong, but the fact that water is a polar covalent bonded substance that makes water dissolve so much stuff. That's the beauty of water. If water were covalent bonded, there'd be no life on the earth. If we go to the moon, Our first thing to look for is ice, where the moon's real cold. Because without ice, without water, can there be life? Or if we know there can't be. So just cut to the chase. If you can't find water, then don't look on that planet because there ain't nothing there. But if you find ice, that would indicate it used to be, there might be signs of life still there. Much in my heart. I want to get through these polar covalents. That's why salt dissolves in water. When you get done writing, see if you can look at what you wrote. Those are not just words, they actually are concepts. What's it mean to be water soluble?
Dissolves?
Water?
Is fat water soluble?
No.
No. So this is not about fat. Is a French fry water soluble?
Most of the time.
Yeah, it's a lot of water.
McDonald's French fries.
Take a long time for it to, though. It will. Bacon won't. Bacon mainly fat. I would have made it 2 slides, but I'm afraid I might lose my train of thought. I did that, so I won't keep it on 1 slide. Once again, remember now, water is a polar covalent substance. Right? Any other polar covalent substance will be broken. Remember the ions? Like salt water, like salt, sodium chloride? That's an ion. You drop it in water, the polar covalent properties of water will get in there and pry those two apart, and then it will circle the sodium, it will circle the chlorine, so they can't get that together again. That's how you make salt water. You dissolve salt into it. Prevent recombining. Now, if you have that salt and you boil the water away and it's all gone, what do you have down there then? Is everything gone? You get your salt back. Think about it. If you have salt water, if you take water, pour salt into it, stir it up. Or if you take now and you just boil it, steam, and now there's nothing there at all except salt. When you lose the water, what the 2 ions do? They come back together. If I put salt back in, if I put water back in there, how do you clean your kitchen? How do you clean your dishes? With water. You put them back and you break it up and you dispose of them. Water is a major. We use it all the time. If you lose your water to your house, how handicapped are you? Big time, buddy. Big time. Big time. Okay, we're not doing this on properties of water because I got more slides coming about water, and I'm going to stop it right there. So we come in, next Monday? Now, be sure and look at that lab course on Angel. I got things you need to bring to class with you, Mark. So far as I'm concerned, that's what we did today. And I'll start number 12 tomorrow. Tomorrow being Monday, of course. Okay, you didn't know what tomorrow means. That's 1:42.
Can you go back to that?